Okay, this is just a bit of preliminary stuff to motivate what follows. First of all, a rational number is any number of the form a over b where a and b are both integers and of course b can't be 0. That's called a rational number, and the set of all rational numbers is denoted by the letter q, which is from the German quotient or something. And if a number is not rational, it's called irrational. Okay. In most textbooks you'll find some sort of proof that the square root of 2 is an irrational number. In most elementary textbooks give something like that. Well, I think we can do better. This is a proof that the nth root of m, where n and m are both integers, and we're not going to allow n to be 0, is either an integer or it's irrational. Okay, so it cannot ever be of the form a over b, where you've taken out common factors here, unless of course b is equal to 1, because if b is 1, of course, then it's going to be an integer. So then, first of all, let's assume that that's assume that you can write it in the form a over b. Then it means that the a over b to the power n is equal to m. Now, what you've done is express it like that and taken out, of course, any common factors between a and b. The next thing to do is to express a and b as a product of prime numbers, and you'll note that if there's some prime factor, let's call it p, belonging to b, then it can't also belong to a, because if it did, you'd better factor that prime factor out. And you'll notice that no matter how many times you multiply a by itself, you'll never be able to take that prime factor out of the numerator, because it's not in a, and it won't be in a times a or a times a either. It'll never be in the top. So you're always going to be left with a fraction, so you can't have it equal to an integer. Okay, that's a pretty simple proof, I think. And if you look at it, there's an example here. You've got 35 over 12, right, which you can write prime factors of it like that. And no matter how many times you multiply it by itself, you're never going to end up with an integer. You can't do, because the 3 down here isn't in the top, so you can't ever divide that 3 out or that 2 out either. So you're always going to be left with a fraction. Okay, a couple of obvious things to say about rationals and decimals. First of all rational numbers can be expressed as recurring decimals. Because if you take a look at this example here, how you'd go about computing this decimal expansion of it, once you get down into these zeros here, there's only a certain number of remainders that you can get when you divide by 7, and if you hit 0, of course, it terminates. Otherwise, you've got only 6 possible remainders, and once you start getting the same one again, the whole thing repeats. That's why you get recurrence, occurring all the time, or it terminates. Okay, if it does terminate, so you've got something like 3/4 equals 0.75, then you can re-express this as 0.74 with 9 recurring at the end there. So there you go, all rationals can be expressed as recurring decimals. Now similarly, all recurring decimals can be expressed as rationals. Basically, if you just go through a process like this, so if you take a look at this here, where the 418 here is the bit that's recurring, first of all you just take out this bit that's not recurring, which is that there, shift all this up by a factor of 1,000, which is what that's doing there, and then re-express the recurring bit like that, and you can take the 418 out, and you're left with this series here to sum, which is really quite simple. If you imagine the sum is s, then s divided by 1,000 is just going to be this here, where you're dividing each term here by 1,000, and if you subtract this from the one above, you'll be left with, well, that will cancel with that with that, and so on all the way down. You'll just be left with that first term there. And this is now a nice easy equation to solve for s. Just take the s out, and you get 1 minus 1 over 1,000, which is going to be 999 thousandths. Multiply both sides by 1,000, divide them both sides by 999, and you get s equals 1 over 999. And so therefore, when you plug that back in to this expression up here, you get this down here, where I've just multiplied the 999 by 1000 there. And if you do a little bit more computation, you end up with that. And I've not bothered to cancel these out. I mean, anyone can do that. It's not the point. I've expressed it as a rational. And that means, of course, that irrationals do not form recurring decimals, basically. I think it was Galileo who first noticed that there is the same number of even integers as there are integers, and it turns out, although slightly more surprisingly, that there is the same number of rational numbers as there are integers, by the same sort of token. And if you look here, here's how you can actually prove that. What you have to do is basically count them, and this is a way of counting all the rational numbers. If you look, you sort of start here and go down here and across there and so on, and sooner or later you'll have encountered every single rational number. And if you happen to hit one that's you've already got, you just don't include it, basically. So you get this sequence out like this, which starts like that anyway. And that's not immediately obvious and somewhat surprising. It turns out, in fact, that this property of being countable is actually quite important, and a lot of proofs in some more advanced mathematics depends on the rationals, for example, being countable. Right, the set of all numbers is denoted by R, and I should probably say real numbers here because I'm not thinking about complex numbers. And of course it includes the rationals and the irrationals. Now, unlike the set Q, the set R cannot actually be counted. Because suppose you could count them, and you could then write them down in a list like this. That's the first, that's the second, and so on. Then all I've got to do to prove that you can't do this is to find one that you've missed. And I can do this like as follows. Construct first of all a sequence of digits, and make the nth digit in this sequence different from the nth digit of the nth number in the sequence, as follows. Make it 1, unless the nth digit of the nth number is also 1, in which case you make it 2. So if you go down this list, for instance, you start with 1, 1, 1, and then because this is 1, you make that 2, and then 1, and so on, all the way down. And then wherever you put the decimal point in that sequence, it doesn't matter where you put it, it's going to differ from every single one of these numbers. Okay, in at least one place. It's guaranteed to be different. So you haven't put it in the list. You see, this of course is an argument which isn't going to work in the case of Q, where I've shown how to actually count them. So whatever rational you give me, I can tell you it will occur in, like the 1000th number in the list or something. I can actually tell you where it's going to occur, but you can't do that with the reals, because in a very real sense, it is a very much a bigger set. Here we've got a sequence of rational numbers whose limit is also a rational number. It's 1 or 1 over 1 if you prefer. Now, in general, that doesn't happen. You can't confine yourself to working just in Q, the rationals. You have to consider the reals, because usually the limits of rational numbers end up being irrational, as you can see from this example below, where the limit of this sequence, it continues indefinitely, is the square root of 2, which we've already shown is irrational because it's not an integer. And this, by the way, is called a continued fraction. It's not of much use outside of number theory, but I thought I'd just give you that as an example. Right, what we need is in fact a clear definition of R, so that we can do limits properly. And this, in fact, should of course start from Q and not assume we've already got R, not assume that R already exists. And what I'll do is make R using limits of Cauchy sequences in Q, and then show its equivalent to the familiar decimal representation of R. There's another way to do it as well, which is equivalent, using something called a Dedekind cut, but I think this way is actually better, personally. Right, I better explain what all this lot means to anyone who's listening and doesn't know anything about Cauchy sequences.